Hi, I'm Mahmudul, and my partners were Darius and Tiffany. For our final project, we decided to implement a caching algorithm called Adaptive Replacement Cache, or ARC. We were interested in exploring caching further because of its importance in data storage system, which millions of applications rely on. Caching allows servers to serve data much faster than if they've been pulled from a larger system like a database. And the biggest challenge with implementing cache algorithm is to optimize for the number of hits, since cache misses are really bad and increase the latency of serving data. In Precept, we learned that LRU is the best performing queue-based caching algorithm on realistic workloads, but what LRU fails at is accounting for the frequency of keys. That's where adaptive replacement cache comes in, and it actually accounts for both recency and frequency, and hence outperforms LRU. And I'll talk a little bit more about the algorithm. So in ARC, the total cache directory is split up into T1 and T2, as well as a ghost list, B1 and B2. The T1 part of the cache is dedicated to entries that have been recently hit, while T2 is dedicated to entries that have been hit at least twice in the history. The value P is an index that marks the partition between T1 and T2, which I'll talk shortly about, and it can move dynamically. B1 and B2 are the ghost lists for T1 and T2, and a ghost list just refers to a history of recently evicted keys for that corresponding cache. The T-list implement the LRU eviction policy. So if we ever need to put a new key into a full T1 or T2 list, we need to evict that key from the T1 list and then store it into the corresponding ghost list. These ghost lists are the most important part of how ARC works, since if we discover that the key misses but was found in B1, then that means that we should have increased the size of T1, since we must have evicted that key in T1 and stored it in B1. Similarly, if it turns out that the key was found in B2, then we should increase the size of T2, since it was evident that we evicted the key from T1, T2, and it was stored in B2. So we should decrease the size of P in that case. Now I'm going to pass it on to Tiffany, who's going to talk more about the testing we did to compare LRU and our ARC.
So some of the parameters we used to vary the cache were the number of requests, the ratio of set to get calls, the range of possible unique keys, and the cache size itself. On the screen here, I have our just very basic control test where the cache size is 20, the range of keys is around 40, and there are 5,000 iterations of a set and get call. We also had a helper function mapped to same that essentially just increases the probability of hitting a specific key, so collisions. So running this test, we see that ARC does outperform LRU by a little bit. So next we manipulated the set call to get call ratio to see if that would make any difference in the results. So essentially everything is kept the same, except now the number of set calls and get calls differ each time, as you can see briefly on this code. So because printing out the results like this is a little bit hard to see, we ran a previous iteration of this test and plotted it on a chart. And as you can see, ARC does outperform LRU by a little bit, although the set to get ratio does not seem to have too big of an effect on the performance of either algorithm. So we also manipulate, and we didn't really do extensive testing with this variable because we wanted to use tracing for a more realistic workload with a larger number of requests and key IDs and larger cache sizes, which Darius will explain now.
To test on a more realistic workload, we used the Wikipedia 2019 trace, a trace of Wikipedia users requesting different documents. The full trace has over 2 billion requests, which we broke down into batches of 100 million requests and evaluated 2 batches. We also varied cache sizes for both LRU and ARC by several orders of magnitude. For this demonstration, I will select a smaller batch of 1 million entries for a quick performance comparison. So immediately we can see for a cache entry count of 100, LRU, the percentage on the left, is a hit rate of 0.8% roughly, whereas for ARC we get a hit rate of about 5.11%. Now, this is around a 5 times performance improvement, which is rather substantial. Of course, as we increase our cache size by successive orders of magnitude, this increase decreases somewhat until we reach a cache size of 1 million, where we get the exact same performance between the two. However, this does show the results that for any level cache, at least for this workload, we observe that ARC outperforms LRU. Even when we extend our data set to the full 100 million request batch, which we pre-computed here in this graph, ARC continues to outperform LRU. ARC, which are the blue data points, eventually reach a very close parity with LRU, with the difference being less than around 1% for a cache size of around 5 million. And eventually, when the returns diminish to the point where there aren't really any more benefits to get out of an improved algorithm whatsoever, LRU and ARC have the exact same hit rate. However, this does show that for a very negligible performance difference in terms of actual cache implementation, ARC outperforms or at least equals the performance of LRU for almost all of the Wikipedia data set, which represents a pretty significant improvement and means that for other production systems, ARC is worthy of consideration.